Well, there are still some stragglers, but let's get started. I think this is Shannon Curry, or rather Vladimir a la Shannon Curry, because that's what I thought I was going to introduce, right? So Shannon leads NASA's MAVEN program at Mars. She will show us how solar activity interacts with the Martian environment, how the solar wind, radiation, and extreme events shape atmospheric escape and long-term planetary evolution. As if you didn't hear about it already, but she's really going to give you the real details and physics. So let's welcome Shannon.
Thank you. Thank you so much. And these talks were so great this morning, great scene-setting talks. And Dr. Spencer really set this one up well because that was such a fabulous focus on. Well, nonetheless, that was such a fantastic talk from like the last time. Actually, I'm going to show some very similar figures, but then sort of in the context of Mars and sort of thinking about the big picture. So I just wanted to start with this beauty. This is the September 2017 storm. It was criminal. We had no assets at Venus, but as you can see at Mars, you know, we had stereo A and we had Earth. And so we had this beautiful, beautiful set of solar system assets. And this was one of many storms we could see around the solar system. And so, you know, a lot of this talk is talking about like how do we explore, you know, beyond Earth? What are the assets we have? How does this affect all of our solar system assets? And how does space weather affect solar system exploration? So one of the themes, you know, from this is going to be from heliophysics to the moon and Mars, and the impact of sun on space exploration. And one of the things that, you know, there are two sort of main points I hope you can walk away with after today's talk. We have solar activity at Mars. And in terms of when we think about like the space exploration component, that's going to affect things like human health. It's not if, it's when we're going to Mars, right? And so when we have crewed flights there, we're really going to have to think hard about human health and radiation. Certainly the radiation dose during cruise and in orbit, right? And so Don Hassler has done some fabulous studies with the Curiosity's rad detector going to Mars, right? But we only have one data set on cruise to Mars, looking at that, and then we only have that one point source on the surface, but that's going to be something we have to look much, much, much more at. We know things like radio blackouts exist, right? When you have a conducting ionosphere, some of those same dynamics, even without GPS yet at Mars, that's still an issue. Single event upsets, so those are called SEUs. Then we have latch-up events. Latch-ups are where you see physical damage to an electronic system. These are very, very serious. We take these very seriously. We've seen both SEUs and latch-ups for robotic assets, certainly in Earth orbit, but at Mars, that's going to be something we think hard about. And then finally, we know that, as we'll talk a lot about, and, we have Marcin Polinsky here this week, he'll be most likely talking about more of this. We see that when we get all of that, the space weather events hitting the upper atmosphere, we're going to get atmospheric variability. So that's going to have a huge effect on things like entry, descent, and landing, and just atmospheric drag. In terms of some of the science, we know that space weather at Mars has a huge impact on atmospheric erosion, on surface atmosphere interactions, things like ionospheric dynamics and variability, certainly exospheric variability. So when we talk about like that extended corona, that's where we're gonna see, that's both oxygen and hydrogen at Mars. That's one of those areas where we also again start seeing our atmospheric drag models just get trashed. And then we're like, oh, we have to do a burn now. I mean, they're very real results from a very cool scientific process, but also thinking, okay, when you have these atmospheres in orbit, especially like an elliptical orbit, you're gonna have to manage them. And so another cool area there. And then certainly one of my favorites, magnetospheric disturbances. I saw talks for the rest of the week. I know a lot of you are really interested in that. While Mars has an induced magnetosphere, it's super cool nonetheless. And there's some wild things that go on that we'll talk about in a case study. You know this, but I just wanted to remind everyone, right, that Mars has these crustal fields in the southern hemisphere, while Earth has this beautiful dipole magnetic field, right? And so the solar wind interaction with Mars, right, you're getting that really like an induced magnetosphere, whereas Earth, you get that Stengy cycle, and you get, a lot, the dynamics look really, really different, especially during storm time conditions. Okay, so brief reminder, because we'll use this nomenclature, of course, both planets have a bow shock, but then we have an induced boundary. So for example, we're gonna have like an induced magnetospheric pileup, and here, like you can start to see, a magnetosheath. A lot of these regions still have some of the same dynamics, but again, at Mars, one of the really interesting things is that these storms, solar storms, both stream interaction regions, which I can't count as solar activity, as well as those coronal mass ejections and flares, those are going to come right up against the atmosphere and interact with it. And so all of a sudden you have a really, really different system, and it's much, much, much closer in. This is not to scale. That'd be a great figure we should make. It's just the scale of where Mars bow shock is to Earth's bow shock. That standoff distance at Earth is much, much, much farther away, right? Because of that thermal and magnetic pressure, those differences, and the ram pressure, right? At Mars, it's much, much, much closer in. So, actually, Mr. Spencer showed this earlier, but this is a figure my students and I made. I was really interested in when, and Vlad mentioned this, where is the most solar activity? So when I first started teaching here at CU and teaching them the solar and space weather class, it's important to not just naively say, okay, storms happen at solar max. I mean, first of all, solar max isn't one, right? We know that that's going to be double peaked, right? As we see those reversals in both fields, right? But not just that, they can happen on the ascending side. But in this figure, one of the things that we thought would be fun to plot, starting with solar cycle 20, would be the solar storms that had either a KP of 9 or an X-class flare associated them with at least an X-class of 10. And so it can be both, but it could be either or as well. And so the flares are marked in these, there we go, in these triangles, and the geomagnetic storms are marked with the stars. And so the KP index, we put the light blue on there because it just had 2 bars originally, but really like a KP of 9, that could be a 9 minus, 9 or 9 plus. And so this is going to be the 9 minus and that minus and that light blue. And the X-class flares, all the way back over, here we go. They start at 10 and go all the way up. And so you can see they're certainly clustered at the solar max, but I think one could argue that we see a lot of activity on the declining side of the solar cycle. There's some really interesting papers discussing why we would actually see statistically more on the declining side as those two magnetic fields are disentangling themselves and some of those shearing forces are starting to decline a little bit. But maybe that's another debate for another time. Nonetheless, we wanted to plot this because, again, you can start to see that they're all over. And so when we think about prediction and how important prediction is, it's not just, first of all, there's not one peak of the solar cycle. And, you know, we need to understand this is just from Earth's vantage point. These are just what we could measure. And I should point out here, you know, in the 70s and 80s, there's going to be sampling bias, right? We didn't necessarily always get to measure some of these storms. We didn't catch them all. You know, we've never had more space weather assets than we do today. So there's sampling bias embedded in a figure like this. That really tells us we need, you know, the fact that we have 1, 2, 3, 4, 5, like, you know, we're coming up on barely 6 solar cycles in the space age. That's a low sample size for us to really be able to understand this problem. Okay, so I also wanted to point out with respect to Mars and Venus, because, you know, these are Earth-based observations. So I'm going to skip up here, and you can see some of the same aspects. So Venus is in green, and Mars is in red. These are plasma observations of spacecraft at either Mars or Venus. I want to point out that, like, of course, there were other, like, you know, things. There have been other missions. However, like Magellan is not on here. Venus, that was one of our, the radar sounding, but that did not have plasma instrumentation. So I think for the sake of this audience, I tried to limit it to either flyby science, and you can see that's when you get a dashed figure, or then dedicated assets. So we can start with Mariner 9, then we've got PVO at Venus there, in solar cycle 25, 24, 23, 22, 21. I forgot these labels. Yes? Oh no, did those fall off? I led those. We'll make sure we add those. Maybe it got whited out here. We most certainly did. Parker Solar Probe, the Venus Gravity Assists. No, I helped convince Nikki Fox that we should do those. Do not tell her that those are not on this figure. I will add those back in immediately. I think those got whited out somewhere along the way. That's actually why I started putting all the flybys in. So 100% yes, we have 7 beautiful flybys. Maybe in backup slides I can sort of show you those. And so in any event, some of the flybys here, and then you can start to see Escapade is up here. I'm the project scientist of Escapade, so I sort of switch hats, and we'll talk about that later in the talk and what Escapade can and also cannot do. But the point of this is really to point out that PVO, VEX, MEX, and MAVEN really did a phenomenal job, and MGS did a really phenomenal job. Those dedicated assets with plasma instrumentation just did such a great job helping us understand stream interaction regions, CMEs, et cetera, and what that looks like at both Mars and Venus. Incidentally, just to sort of ruin the plot line, they have really, really different interactions just based on their distance from the sun. One of the reasons, just as on the science side of things, are the human spaceflight's a little bit less interested, but you know, I am a scientist. One of the really cool things about these solar storms, especially the big ones, is that it gives us a little glimpse of what we think the early sun looked like, right? We do think that the early sun was more active. Yes, we know about the faint young sun paradox, but I'm gonna go out on a limb and say that even though there are those that believe there was that magnetic envelope that might have suppressed some of those storms, there's a lot of reason to believe that the sun was in fact more active, just based on things like looking at Mars's atmosphere. I'll tell you about that in just a minute, but the fact that so much of Mars's atmosphere was stripped away does tell us that that has to happen through interactions with the sun and some of those escape processes. And the storms that we see now could offer a glimpse of what almost regular, like nominal, stormy, catastrophic conditions may have looked like in that first billion years. Right, the sun was spinning faster as it's spinning down, losing angular momentum and mass. So we know that we have a slower rotator than we did 4 billion years ago. And I would just like to see that as it's a really cool way to start thinking back in time when we think about like atmospheric and planetary evolution. So I am going to talk a lot about MAVEN today. MAVEN was designed to, at Mars, look at exactly this, looking at the Martian atmosphere and how it responds to solar inputs. This is both a wonderful thing and a horrifying thing. MAVEN is the best observer of atmospheric escape in our solar system. We should have one at Earth, mind you. We don't, but that's above my pay grade at the moment. Nonetheless, we've learned more about the physics of atmospheric escape and why the sun is the main driver of those than we really have with any other mission. And so it's got this really incredible instrumentation suite that's able to give us a lot of information about the real-time physics. So things like the EUV, the IMF, right, the solar wind particles, and then understanding what happens when a storm propagates past Mars and then what its atmosphere is doing. This is our instrument suite, just in case you're interested. So we'll talk about this later, but with the sun and the solar winds and storms, we can see we have a magnetometer, we have an electrostatic analyzer, ion electrostatic analyzer, we have a SEP detector. So we can really get all of the particles and fields from the sun, and we also have EUV, so we can monitor those flares, which are really, really exciting. We have a Langmuir probe, we have some heavy ions, and that really helps us see the atmosphere. And then we have our beloved atmospheric, one's remote sensing, that's an ultraviolet imager, and then we have NGIMS, that's an in situ neutron spectrometer, mass spectrometer, not neutrons. Okay, so this is a figure many of you might recognize from one of the Nexus studies we did ages ago. So I'm going to focus on magnetized planets. But one of the things hopefully everyone can take away from this, and I know Robin Romstad's going to talk much more about ion escape tomorrow, especially with a fun case study, is that the sun is driving so much of atmospheric escape. This is important because it's not just, if the atmosphere is escaping, one of the things that we're going to circle back and talk about when we talk about the May 2024 storm is that, well, I'm like, wow, this is so cool for evolution. But then I've got my project manager who's like, I'm sorry, the atmosphere inflated to where? You know, that means if the atmosphere is escaping, that's going to be more drag, right? When the atmosphere is inflated, that's going to be more drag on a spacecraft. And so somebody's nightmare is somebody else's wonderful, wonderful fantasy. And so I would just briefly point out that, some of the escape processes here that bring us so much joy as scientists, it's really worthwhile to think the operational side of this has a lot of vested interest. But just to quickly point out some of the escape processes that the sun derives, we have genes, photochemicals, sputtering, hydrodynamic escape. And then with ion escape, we have things like polar wind, ion outflow, auroral winds, and pickup ions. You can see sort of this branch here on the unmagnetized and then what we call the both. And so here, those are the escape processes that at Mars we're really able to study. One of the really cool things, and it's not a Venus talk, it's a Mars talk, because truth be told, I don't think humans are going to go to Venus, so today we're not talking about Venus. But at Venus, some of these same escape processes don't actually happen, even though it's an unmagnetized planet. So for example, thermal, a lot of the photochemical escape, and a lot of the, and even barely ion escape, those are not things that work well at Venus. And so at Venus, because Mars is smaller in size, we can study the physics of this much better with reaction to the sun. This is important when we also think about star exoplanet interactions, just to sort of seed that. At Venus, things are too heavy. They're gravitationally bound, so one of the only ways to get heavy ions out is through ion escape. So one of the things that's really cool about space weather, and as we go to study all of these kinds of physical processes when we think about atmospheric evolution, one of the cool things is that we get to see storms, and I say we, meaning Martians, so we're all going to be Martians today for a moment when I say we. We get to see solar storms and space weather events that you can't see from Earth's vantage point. So this plot is busy, but we're just going to talk through it. This is the mission timeline on the bottom. So we went into orbit at the end of 2014. The red dots are CMEs, the blue dots are stream interaction regions. SIRs and CIRs are the same thing. CIRs just mean the co-rotating interaction region. That just means they make it around the sun once, by the way. So basically the same thing. And then yellows are hybrid events. that's when we see these two events merge, and they merge all the time at 1.5 AU, and these things are bonkers looking. So, okay, if you look on the left axis here, so this is the Earth, Sun, Mars angle. So 0 means we're kind of looking in the same place, and at 180, that means that Earth and Mars are on other sides of the sun. So basically, all of these events, mostly like above 135, were more or less not visible from Earth, which is not always exactly, because, you know, where on the disk it happens, right, and launches from is going to have some play. But there are a lot of storms here that were not visible from Earth, but that MAVEN was able to clock. I would point out there is a small bias here, a sampling bias. In 2020, we went through something called aerobraking. We had to shrink our orbit to help relay more of the data from the rovers. Blah, 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 blah. It just means that we're not in the solar wind quite as much, so we missed some of those storms. It's not that there are less events happening or less density. It just means that our orbit we were voluntold to do a little bit more for the relay piece and a little bit less on the science piece, but just wanted to clarify the density there. And then if you come over here in green, that's the sunspot number, just to give you a sense of where we were in the solar cycle. Okay, so here, right, we were in the tail end of solar cycle 24. We went in that bonkers deep solar minimum. We were sort of jazzed for like a lot more space weather, but we started seeing more events, believe it or not, as we got into the ascending side of solar cycle 25 and that peak. Okay, so this is just sort of a fun one. I have to fill it in even more. This is, like, these are the solar energetic particle events. As our previous speaker mentioned, one of the really cool things is that, you know, you've got flares, that's really important, but when you start to look at particle acceleration, right, I won't get into it too much here, but particles can get accelerated a few ways, right? You can have just an SEP event. They can also be accelerated by the shock front, right, of a CME. They can also be accelerated actually when a stream interaction region and a CME merge. There are actually a couple of ways to do that. And so in any event, or they can, you know, get fast-tracked, you know, they erupt from, right, that footprint, and then they can attach to one of the field lines, and they can rip down that field line and sort of like on an express train sort of get there. So there are lots of different ways for particles to get accelerated, and I think there's this idea that at Mars they slow down, but that E.dl, the DL there gets longer. And so that's not always the case. You can just get some really, really, really intense solar storms at Mars. And you can start to see, here, up here, this is again that declining side. This is like that March 2015 storm. Here's that September 2017 storm. That was like the biggest flare in CME we ever saw. Haha. Until 2024, and then between 2022 and now, we've just seen sort of nonstop activity, and that 24 storm was really, really something, and we just did a special issue on. Really cool. But you can see there was a window there that was in 2018 to 2020. We've just mushed onto this. It was very, very quiet. Now, that did allow us to study lots of other fun things, but in terms of the solar activity, it's really picked up recently. Okay. This is another way to just sort of look at when we were talking in that earlier figure about storms you can see from Earth and ones you can't. So I'll start with, if any of you know Longian, she's at Goddard. She and Chris Russell developed a really cool metric called the total perpendicular pressure. So I'll just start over here on the left first. So one of the things about the ram pressure, when we sort of talk about the ram pressure of storms, is it does neglect thinking about the magnetic pressure. And so what they did was they actually have PT being, right, here we go, here's that magnetic pressure, and then you're gonna get that thermal pressure. And this is actually the perpendicular component of both the ions and the electrons. And so this is a really nice way to, in my mind, categorize the strength of a storm, because often you'll see like a big magnetic field perturbation in a CME, but then like lower densities and velocities, and then vice versa. At the end of the day, though, nonetheless, PT, you know, the stronger the pressure, the bigger the storm. So here, these concentric rungs in this figure, we like made this figure up. Feedback is welcome. If you think this is terrible, just say so. We won't use it. But this is 10 out to 300 picopascals. Yes, it's pico, not nano. If you do the math, the nano Teslas get there. Anyway, doesn't matter though. Nonetheless, you can see this, the farther out you get, the stronger the storm. So that's what those rungs are. Then you've got here down, oh my gosh, here at 0 degrees, if Mars and Earth are both right there, they're more or less, right? They're right by each other. That's actually a great time for a Mars launch window. But nonetheless, and then 180 is up here, right? And that's when we call that solar conjunction. You're on the other side of the solar system. More or less, that's when we don't see those storms. So actually the May 2024 event, we'll talk about it. When that solar active region rotated off the disk, right, off the western limb towards Mars, we got to see stuff that nobody else did. It was super cool. Okay, so you can start to see there are a lot of events, right, that we saw at Mars that, again, were not really all that visible from Earth. And if I then say, let's just like black out all the stuff in the middle, those are fun storms, you know, but there's sometimes like a 10 picopascal storm is kind of like a baby storm. If we want to see like the big kids, that's where we're seeing a lot of these. And the strength of these in particular, we're seeing a ton of events all back here between 90 and 270, right, that weren't necessarily visible. So one thing I do want to point out, that is the May 2024 event. So if we take a look for a minute, this was MAVEN's orbit during the 2024 event. Well, here's the storm. And there you can see it. It really hit Mars head on. So I'm going to do that like one more time. And you can see Earth is in yellow. So Earth is here, as you can see, as we always do these frames, right? And then we've got Mars out here. So when we look at that event, we saw this really, really beautiful, like head-on propagation past the planet. That for us was really exciting. And so here was MAVEN's orbit. Over here, we have an elliptical orbit. Our periapsis was in the northern pole, and our apoapsis was in the southern pole. So we did get to see that solar wind down here. The shock isn't on here, but we were outside that shock. So we got some really nice measurements of this. So what happened? So this is sort of interesting. This is where these were some of the events that we actually, like the CME and this X-class flare, were actually not well observed from Earth at all. So there are 3 X-class flares in quick succession, followed by an X6. We then saw a CME, and then we think that X16.5, that has not been well calibrated. If you do know it, come and tell me. I've been not following quite as much in the literature. And if you wanted to just quickly look over here, those are the SEP ions. Those are the super high energy, right? That's KeV. We have the SEP electrons. That's the solar wind velocity. Here you can see that ion energy, the electrons, and here's that magnetic field. And so you can certainly see the disturbance down here with that CME. And over here you can start to see, right, the X-rays were captured by our SEP detector. So this is the effect of the May 20th flare on the Mars thermosphere. This was really bonkers because some of the IUVS observations of CO2, basically the doublet emission, showed a huge enhancement from the previous, like that X8.2 flare that we had seen in 2017. So what I'll do is I'll sort of show you over here. This is the pre-flare. It's in gray. It's sort of hard to see. And the post-flare is over here. We got to have a real-time, like orbit by orbit, we got to see this is a big enhancement in terms of that thermospheric increase. And so here, this is actually what we saw in the flare in terms of the radiance versus altitude here. And obviously, this is sort of reconstructed. So one of the things here, if you look, here is that flare orbit, and we've got to darken that. That might be a little late. And we saw a 70K increase. I mean, that's really a huge difference in the thermosphere. It puffed up a ton. I mean, I'll say this much. Had there been like crewed flight in orbit or crewed assets for, hypothetically speaking, like a new Mars telecom network or something like that, that would have been something to keep a close eye on because the thermosphere inflated significantly, right? We know that KT over MG, right, that scale height really heated up the atmosphere. So again, this is a nice way of looking. Here's the latitude and here's that temperature. So again, the blue and the black are the pre and post flare measurements. You can see during the flare, we saw a huge, huge, huge peak we saw a huge peak in that thermospheric temperature. So just a big thanks to Sanal for putting that together, and the whole team. It was extraordinary to see. In terms of the flare activity, Ed Tiemann and Alex Kramer did some really cool work. So this is GOES data, and then here's EUVM. Now it does saturate, but you can actually see these 3X class flares here, and we can again see a huge difference, right? So here we're looking at the CO2 density, and here's the altitude. So we saw an enormous density enhancement in the CO2, and then a massive depletion after. And so sort of the takeaway here is if you look at like that baseline, and here's that flare orbit, again, we saw a massive difference in those densities going way, way, way up real time during the flare. We often ask, like, what really happens during a solar storm, right? Because a CME, that time scale is on the order of what, at least hours, but more like days. Same thing with the stream interaction region. Flares are much shorter time scales. We are seeing from orbit to orbit a difference, right? So that orbit to orbit difference, like this is real time, like up and down. And that really tells us, in my mind, the need for space weather prediction and real time, like real time alerts. We're not gonna have, on this kind of a time scale with light time, we're not gonna have time to send stuff back to Earth. This is where I think the Eddy Symposium, thinking about AI, thinking about automation, and what we know about space weather and creating like basically flags on board, that's gonna have to be necessary for something like Mars, because if this were to happen there, you can't send it home, analyze it for 12 hours, and then send it back. That's even an hour. I mean, light time is right, often like 20 minutes each way. That's out of the question. So this is a really, I think, a great example of that. And we'll talk about, a recent example, and we'll talk about Escapade in a minute, but like with Escapade, we actually did have to sort of stay up all night and do like a real-time event analysis the day of launch, and I'll tell you that story. But that's just not something we could do here. This will require AI. This will require like heavier thinking than we currently have on board any of our flight computer systems. Oh, yes. So massive Lyman alpha increase. This was just bonkers. Really, really fun. Would have been awful if people were there. So, okay, so this is another just example just to give you like some just general understanding in terms of when we think about like what we saw, right? So here, this is our, again, mission timeline. This is our SEP FTO counts. Really just think of those as counts. Here's our March 2015 event. We all like hit the roof and celebrated when that happened. And then the 2017 event came and we got really excited again. February, we started seeing, here you can see solar cycle 25, defying all of the haters and being like an actually fun solar cycle, not a quieter solar cycle per prediction. And here is that May 2024 event. This was the biggest event since the since basically that Halloween storm 20 years prior to that. So this was a big one. And we were just really excited. And again, while it was happening real time, it was really, really, really fun to be a part of. Here I would also point out those ions were well north of 20 MeV. At some point our detectors saturate, so we don't know how high they went. We can try and back some of it out, and certainly some of the other assets have helped us do that. But this is another great example of like having a true high energy detector at Mars on board in flight is critical, as well as making sure some of that automation is there. The sub-event did observe flares though, and this is kind of a cool trick from our instrument lead, Ali Ramadi. So one of the cool things was in May, at this point, I think that these were not necessarily visible from Earth anymore. You can actually look at the counts. So here are those counts, right? Here's that SEP. So you can see this signature. Those are the background X-ray counts from that first flare. Here, you can actually see a double flare. It's hard to resolve, but again, if you look at our counts, you see them back to back, just separated by about 20 minutes. Again, another lovely example of why you cannot ship this back to Earth and then back over when you're on the other side of the solar system. And then finally, this was the big one. This saturated and it was missed by EUVM, but this was one of the, this is a great way. Our SEP detector has a much more forgiving field of view, and we were able to see some really, this flare, and this was certainly the largest of all of them. And by May 20th, that active region had totally rotated off the disk and was no longer visible from Earth. Oh, here I should get closer. So yeah, this was work from Ali Ramadi and then Devin, his student. So, and then I'd like to save some of the fun stuff for last. Okay, so if you look at the run up to the flare, a lot of times we can see aurora. And so so at Mars, we have 3 types of aurora. Maven's actually been able to discover one and a half of them. And so all of these SCPs were driving aurora at Mars in a really cool way. And again, circling back, you guys know this, because there's no magnetic field at Mars, we got these we'll just say it's a really, really different system. So you can have diffuse and discrete aurora, but the whole thing lit up. So I'll just sort of show you this movie. We're just clocking along, doing our own thing, and then the whole disk lit up. I should clarify, oh my God, it's beautiful. Had she been an astronaut, this would be visible with the naked eye. We did a study not long after this event where, because of, we're all space weather nerds and blah, 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 so we wrote Perseverance. They have Mastcam Z aboard, and so we were like, hey, if we know a CME is coming and we measure it, can you guys point your camera when you're on the night side up at the sky to see if you can actually do a visible imaging? And at first were not huge fans because space weather and geology are not like best friends yet, but nonetheless they went along with our antics, and then they were able to observe like this beautiful pea green, like the first visible light aurora. So if you're interested in this is something astronauts could see. That's a really, really fun paper between Perseverance and Maven. Again, we don't always get to have experiences where we have like a joint observation if it's not a comet, but this was a really fun one. Okay, so I did want to point out here that flare triggered the direct-to-Mars SCPs that arrived within minutes. Again, these things go ripping down those field lines and just wreak havoc and fun for all of us. We, unfortunately, some of the instrument noise, there were some places that interfered, but we were able to actually detect that full aurora. The intensity decreased, but most of the particles getting to the surface were actually not depositing that much energy. Now, I say that one of the really cool things we get to do with Maven is watch all of those particles, basically like the attenuation as they actually hit the surface. And this is from Nick Schneider and the IUVS group. We know this because there's some other bonus Mars observations during that 2024 storm. One of them is the background counts with HEND. So here, this is the May 2024 event. This is going into a publication soon. We haven't actually gotten there, but you can see this. Really, this is in hours, a beautiful, beautiful, beautiful peak. And just to sort of, again, if you were to look at that, 2004 Halloween storm, the 2003 Halloween storm, you can see Odyssey here, the background counts with HEND. All of a sudden you go to here, and this was the next biggest storm just in terms of those background counts. So Odyssey was actually able to measure the same storm, albeit indirectly. And again, that was from Jeff Plout and the Odyssey team. And then, of course, this is Curiosity. And so those white flecks we call snow. And so that's one of the things, like this is not, some of it's dust, but some of that's actually snow in the detector. That's because some of these high energy particles were in fact able to make it to the surface. And, I think it's been mentioned, but this would be the equivalent of 30 chest x-rays in one dose just from one of these storms. This is also a series of storms. So I think when we start to think about, again, crude health, AI, and how we start to get, how we do our predictions better, this is a great example. I don't want 30 chest x-rays. I hope you don't either. Not in one dose, not when you're on Mars. So especially since not a lot of water, So that's one of the areas where we start thinking about, for those of you interested in like magnetometers and things like this is where like lava tubes and caves, and actually, funny enough, we've been able to ask our geology colleagues to start thinking about like, seriously, like where would you hide during this? This is a nice example of like, we would have to be thoughtful about what to do in something like this. So again, Don Hassler and Curiosity, thank you to their team for providing that. So just to sort of wrap up here, where we were on when we think about impact on human exploration, one of the things is that we're going to see extreme density enhancements, extreme atmospheric heating, right? We saw that 70K increase. Like those SEP events, again, greater than 20 MeV, we really need to be able to constrain that better. And then certainly we see all these incredible aurora, but things like entry, descent, and landing, atmospheric drag, certainly human health, all of these, while these are such fun storms for us as scientists to measure and think about like the structure of these storms and what's happening real time, they're very, very real operational needs for Artemis and the Moon to Mars program. Just a few more things. I think I have a smidge more time on sort of escape, some of the cool things that I've really liked to study. When we think about what this actually does, I won't say too much about this because Robin Ramsad's going to be talking about ion escape. But again, we can take a lot of the lessons learned during these solar storms and apply them to other planets, Venus, Titan, etc., and other bodies. But one of the really cool things is that these ions, that ion escape goes way up during solar storms. It's worth noting, it's not just ion escape, it's ion precipitation. So sometimes on that first gyration, as those ions are, gyrating around the magnetic field line, they can actually crash back into the planet. So you can see some of them might, here we go. Some of them might leave, but some of them can actually crash back in. So these are MAVEN observations of, here we go. This is the solar zenith angle. 0 degrees means this is the sun. Basically, this is like the day side, and this is the night side. Same thing here. 0 degrees is the day side. 180 degrees is the night side. So when you look at escape, you should expect, right, there's more escape coming from the tail. And if you look at the red, that's when we're looking at a solar transient event, and the blue is going to be like a nominal orbit. And then if you look at the precipitation, it's the opposite. On the day side, right, on the day side of the planet is when you expect the most ions precipitating and crashing back in. And you can see generally that those red circles during the solar storm events drive the most precipitation. Robin will tell you about escape, but one of the reasons I get so bent out of shape about precipitation, one of the cool little side things, is sputtering. Sputtering had never been observed before, but we knew it was a solar-driven process, and a process we think may have been like responsible for some of the most atmospheric escape at Mars, and then some of which is at Venus. So basically you have a heavy ion, right? It comes crashing in, and it's kind of like doing a cannonball, right? And so we'll talk about isotopes in a minute, but we know that isotopes, from argon isotopes, that sputtering has happened. We just never observed it in real time. So again, this is kind of what it's like when you have just like quiet solar wind conditions. It's like throwing pennies in a fountain. But obviously when you have a solar storm, it's like doing like a massive, massive cannonball. And one of the things is when we traced argon 36 to 38, just the 2-second isotope piece, right, scale height. 36 sits higher in the atmosphere, argon 38 sits lower. That's just lighter species sit higher in the atmosphere. The 2 AMU difference, just to pick off the top of the atmosphere, can't happen through hydrodynamic escape. The only way you can do this, and the only place it's ever been measured, is basically at Mars. And so when my predecessor, Bruce Joukowsky, did a beautiful study. He looked at these ratios and he found that there was way more argon 38 than argon 36, right? So if you take that ratio, basically we saw a huge increase in that. That basically means that tiny little species off the top, like it's kind of like eating the frosting off a cupcake. Somebody had just gone and done that, and that somebody is the sun. And there's like all of those solar wind particles and particles precipitating in. So this is a really cool way. This is just a real-time example. This had, again, never been seen in any other planetary atmosphere. I wish we could. Up here's that PT factor again. So here's that storm coming in. Here's that solar background convection electric field. And then here's argon. Argon is a noble gas. It should react to nothing and never care about the sun. But here we see this beautiful enhancement real time as we see this storm come through. And it's not just because it's getting lofted. It's actually, this was a cool solar storm that came. This was actually starting to escape because getting all the way up to like 350 is pretty hard. You can't just do that from heating. That actually requires like collisions, and those have to be sputtering collisions. Photochemistry doesn't do that. Yes, so we saw an increase, by the way, of about 10 times the nominal. So these solar storms have a huge, huge impact. And again, Robin will tell you more tomorrow about some of the reasons ions are awesome when they leave. Just wanted to quickly just highlight, MAVEN's done a ton of work when we start to look at actually some of the stuff we've done. There's that beautiful green aurora, right? We've looked with Hubble, This is when New York Times was nice enough to say Mars got cooked by a recent solar storm, right? So this was our, that was when we make the New York Times, for plasma people, we like really celebrate it. That was very exciting for us. Solar storms, again, we did like a fun thing. Actually, right before the 2024 event, I convinced JPL to be like, we should be getting excited for Solar Max. And we did a really fun article with them. And then certainly more. And then, of course, I would point out, with the stream interaction region, granted, it's not necessarily solar cycle dependent, but at one point we saw such a strong SIR that it basically, like the ejecta, right, region behind it kind of like blew out all the solar wind. And so when that went by us, basically there was no more ram pressure pushing on, pushing the bow shock back. So the whole atmosphere like inflated because nothing was doing that. And so we got this call, from our spacecraft team, and they thought we thought we had done an accidental burn. We're doing like a nosedive into the atmosphere, but none of the telemetry said that. And we realized the solar wind disappeared, but the atmosphere just like ate up the whole planet. It's a great article if you get a chance to see it. Yes.
Something like this happened on Earth.
Yes, it has.
Have you compared these two events?
I have. I just didn't make a slide. I want to talk about like all of these are like its own hour-long talk, and I'm already like, it's super cool. Like it's so cool when you have like just bonkers ram pressure or that, that thermal pressure I was sort of talking about. But then also when you remove it, these corner cases are so cool to study as a scientist, but then again, have very real, the irony is that both you take the solar wind away or you turn it to 11. And in both cases, you get this like bonkers atmospheric drag on the spacecraft where we had to kind of like call it in and explain what happened. So really important to study both cases, believe it or not. Okay, so Escapade. So I'm going to switch hats. I'm the project scientist of Escapade. I just point out it's a twin sat. It's a low-cost mission. Like really, it's Class D. And somehow we were able to load it up with some really cool space weather instrumentation. One of the big things, Maven is my baby, but I will point out it is one spacecraft and with a 4-hour orbit. Even, you guys know this, space weather events and looking at the solar wind time frame, you can often, MMS takes things apart on like the sub-second time scale. And so here, with a 4-hour orbit, you get what you would get, when you have here's the solar wind measurement, 2 hours later, here's what happened. You do have to have some guesswork that nothing changed too wildly, or you can generalize it. But with 2 spacecraft, we're going to do super awesome things. Science Campaign A is in February of 28. Don't quote me on this exactly. It's probably going to change. But it goes to August. We call this a string of pearls configuration. So basically that just means we keep the spacecraft within 30 minutes of each other, and then periapsis is 160, apoapsis is 8400, so that's a much bigger orbit than Maven's. It was our original orbit, and even then some. This will be super fun. We transition in hopefully August. We drop one down, and the other pops up, so now we get this gorgeous spatial separation. And then we'll go to Science Campaign B, right? So now, here on one of them, we can look at those shorter time scale processes. One of the really cool things, if you're, more of a solar heliophysicist, is we can look at storm structure here and start to look at some of those differences. And so the structures will be incredible to see real time. But here in Science Campaign B, that's going to be like August till January of 29. One of the really cool things here is that split, we'll be able to see, when I say real time differences, we'll be able to see what's happening. It's like, the sheath structure or the shock of a CME is propagating past the planet, and then exactly when we see the moment of acceleration down tail. So that's just going to be super, super, super cool. Stay tuned. And we want to really include as many people as possible in this. It's a low-cost mission, so we have a lean science team, but we love collaborators, and we're very friendly. So come and talk to me and Rob Willis. So this is just a super fun movie. Yingxuan Ma helped make this. She's an MHD modeler. I love the modeling. This helped us visualize to the administrator and other people why it's so cool to do this. Magnetic field lines are hard to jazz up, but we thought this did a great job. So here you can see our spacecraft starting to orbit. I think we stick to just the string of pearls here, but you can start to see just like in a real-time simulation just how important it is to start to be able to measure some of these different structures. So we'll be measuring escape. We'll be measuring some of the just like, we'll call it like plasma pressure partitioning, where the shock, the sheath line up, and then we'll certainly be able to look at things like the solar activity that's coming in. Yes, we know we were supposed to launch, we'll just say earlier than we did, but for all sorts of fun reasons, I can tell you over a beer, we did not launch when we were supposed to. We did launch in last November. It was really, really great. Some of you in the audience were there. And nonetheless, we're excited to see that solar activity will be on the declining side of solar cycle 25. But as I showed you, I think there's reason to at least cross your fingers that there'll be some really fun activity we'll get to observe there. Okay, so all of this is one of those things where there are incredible operational reasons, for us to be observing, but also when we think about, since a lot of this workshop is dedicated to thinking about, star interactions with a planet, I do want to point out water is one of the biggest ways, like one of the most exciting things to be able to trace atmospheric evolution. We still don't have a great handle on because it requires understanding like the outgassing, the formation of an atmosphere, like with volcanic activity, how that could even have, when you have enough atmospheric pressure, then you can have liquid water. But then if you erode that atmosphere away, that's when the water goes away. So when we start to think about some of our exoplanet and some of these other systems, it's really important to think about the lifetime of an atmosphere, and that's driven by the sun, the photochemistry, and so much of it with the ion escape, because the photochemistry can happen at Mars, but no, really, if you get any bigger, the escape velocity is too high. It'll look something like this. When we think about the escape velocities in our solar system, here's the escape velocity, right? And here's the temperature and the size of the planet. Nothing's leaving Jupiter and Saturn, or Neptune, or Uranus for that matter. But here you start to see that escape velocity get much lower. Here at Mars, right, when you start to get really low, there are a lot of really interesting objects, in particular like Titan. When you start to see objects smaller than Earth and Venus, you can get way more physics. And so again, understanding the EUV of the star and that and those stellar winds, we're at such an exciting point where I think some of the models, and especially with some of the web observations and hopefully with habitable worlds, we'll be able to capture much more of the real physics and not just guess at what we think is happening when we actually think of habitable worlds, right? When you think, I can't comment on oceans or like frozen worlds, but the lifetime of an atmosphere is a major, major player. So while we will not have space weather observations there, we can learn so much about this solar system. Okay, I think I'm supposed to be wrapping up. So I will, with conclusions, I just want to say we've had so many spacecraft really pave the way for thinking about what we know about atmospheric escape and some of the science there. There's so many cool dynamics that happen when we have these space weather events propagate past a planetary atmosphere. We certainly need more measurements to keep understanding how that could affect things like other stellar systems. But also, I would say, as we sort of turn, if we turn outwards and we think about exoplanets, we can equally turn inwards, face back at Earth, and think about how are we going to protect our robotic and our crewed assets, right? As we start to understand more about things like drag, radiation, and just what the effects of that space weather environment look like at Mars. So with that, thank you. It was sort of a core dump on everything Mars, so any questions are welcome.
I have some.
Okay.
Okay, I'll start. So really, I'm thinking of the, atmospheric escape process, right? I mean, that's the most important thing MAVEN has done, and Escapade will show. So my twofold question. One is, how much of Mars's fate is really about losing its magnetic field, and how much is about the sun it was exposed to in that early phase? So that's kind of bringing
sure.
So that's one question,
Okay.
and the next one I'll ask both, and then you can figure out. With the volume of MAVEN data that you see, do you actually think of utilizing AI, or its role basically in identifying the escape process? And if you're interested, talk to to us.
Yes. I'll start with the magnetic field. So we think that around like the 4.1 mark, maybe even earlier, there's sort of like here's that early cataclysmic period when I'm going to call it sort of like, that's the bombardment and hydrodynamic phase. I ignore that. It's chaos. I have no idea what happened. I won't even think about speculating because I won't. But funny enough, that's right after that is when, I say right after, like 200 million years after, is when we think the loss of the dipole magnetic field occurred. Now, there are different schools of thought on whether a magnetic field truly can shield an atmosphere or not. However, I think personally, I think the role of the sun and a more active sun would have had a more significant effect on eroding that atmosphere. We look at the difference in escape rates, and we see up to 2 orders of magnitude difference across the board. So the photochemistry, and I think, I don't know where that figure is I showed you, but the photochemistry, the sputtering, the ion escape go way up when you have increased activity from the sun. And even with like a dimmer EUV, that doesn't change the fact that when you're seeing storms, and it's not just more intense storms, it's more of them, higher cadence and more intensity, that has to be something that I think if I had to put money on one or the other, like in a Mars science betting scheme in Vegas or something, that's where I would bet you'd see the more dramatic influence on ion escape. That said, though, the escape processes at Earth, that's something I've said before. We need to. There have been a few proposals to do so. Some of you have probably been on them. That needs to go through. I think it's both comical and outrageous that we have not studied this more on the one planet that is in fact habitable when we think about a habitable world. The second piece of your question was, remind me? AI. 100% yes. 100% yes. There's so much data. The sputtering thing, I had to keep enlisting students to keep looking for. It's like a whole other talk. But some of the things we've had to look for are really tricky. For those of you familiar with Bayesian statistics, we have solar wind proxies that use Bayesian that do a beautiful, beautiful job. And even basic particle and Kalman filters do a beautiful job of things like, hey, when our apoapsis is not in the solar wind, but you've got the sheath, does this look like other times in the sheath? And you can start to do really cool mapping there. So there's so much room between solar wind proxies, between trying to to identify events that are sort of hairy. And yes, I can think of a top 10 list that AI would be an outstanding place to really, and I know we use the word AI loosely, but really some of the Bayesian work that I've seen out there can just do an exceptional job of picking things out that we're just not able to, even with an army of students. And so this is always I actually gave a Maven AI talk here in 2021. This is so the right community to start thinking about how we do things faster and also more robustly. It's not just about speed, it's the robustness of catching some of these looking for abstracts and large data sets of numbers. Yes, we are. It has changed, and on that front, in a good way. So, yes.
Oh, my first question is, because my original research is actually working on atmospheric escape on Earth. And I was very sad for my whole year spending on the atmospheric escape, especially when you look at Lika's slide this morning. There's no mission right now in the magnetosphere. In terms of the atmospheric escape. We have MMS for sure, but they are not advanced, they are not new missions. There's just no mission. And when we look at, heavy ion escape, atmospheric escape, I think the last time we have such a mission in Earth was back in Cluster, which was dying and ending right now. And I just echo with what Sharon talked about it. It's very sad. We have very little understanding about atmospheric escape right now in our geospace environment.
Yeah.
And then not to mention that, and I see there's a gap when we talk about, for example, moon explorations. And there's some study from the lunar science, they say, well, we believe some of the materials we see from the moon is coming from the Earth, And that essentially coming from the atmospheric escape. But
Yeah.
because we don't have sufficient data, it's very hard to identify, and everything is just based on imagination. So I highly echo, and
Yeah.
I want one of the great scientists in our field, Rick Chappell, he said his biggest dream before he already retired, so I don't want to say the next step.
Yeah.
But his biggest dream is to see someone
hear you.
proposing and successfully launched a mission on like atmospheric escape. That is biggest dream. And my second question is more like, for example, when the Earth and Mars in the similar like, for example, when the Mars in the good launching window. At all of the, you have this slide from 2015 to like right now with all the CME. Is there any event that is conjunction study from both Earth and Mars? And like when there's a CME coming or like SIR or CIR, you see something happening on Earth but not quite happening on Mars or like opposite side. Do you see such an event before, or is not like quite well studied and requires more comparative study between two planets?
So I'll start with the first one. Yes, in terms of Earth mission, I mean, I will say the Carruthers mission just launched. That'll help look at the corona. And so that geocorona is a nice, I don't call it like a tracer or a marker, but certainly there's a lot to be learned about the geocorona and what might be happening with escape, but it certainly is not the same as looking at escape itself. It's certainly it's a product that's informative. There's also GDC, right? So GDC, everybody's hopefully familiar with, has sort of come on and off line because of the fiscal environment at NASA and with the government. So GDC would also be a really important asset with the constellation science to look at those types of things. Again, not quite dedicated to escape itself, but looking at the global dynamics with a constellation certainly helps, and there'd be a lot gleaned from that. You made the final point of sometimes we look at downtail. So there's like a Fillingham study that looked at, I think it was using Themis data. That's all like O plus, like yonder. Yes, you're exactly right. Actually, Escapade's there right now doing a special campaign. And so there are folks who may be online. We're hopefully going to try and shed some light on looking at the deep tail and what we would see there, especially on the heavy ion front. But you're exactly right. That's something that we need to be looking more at. And I support anybody who needs help or wants like a thumbs up or I don't know what, like you have my full support. Or maybe that'll be like the next chapter is for at least me, because I'm not retiring in the immediate future is that. So then then the final point would be, I'm trying to think of what was your second question or second point? Oh, the conjunction saw. Yes. Something that rhymes with flipper, and Maven just had a major paper accepted in a major journal looking at the same storm, but I can't talk about that anymore. And then there's also a really great study by Olivier Vitas years ago. I want to say it was 2016, 17, somewhere in there. And he did a beautiful paper on looking at like multiple observations from different spacecraft of the same CME. But those are the two that I know of that really looked hard at looking at some of that structure. But it's something we should definitely be doing more of. Looking at the evolution of these structures as they propagate throughout the solar system is critical, again, for the forecasting process. We really don't have a good idea when we use the CCMC and we use some of the ENLO models to look at like the arrival times for storms. They do a great job. I'm not throwing stones, but they're often hours to days off, and it's hard to even map them. So when we have a space weather catalog that my student just submitted, and will hopefully go online soon, of all of the space weather events we've seen, you can pull all of the CCMC, like what we think are the analogs, and it's hard to even line some of them up. And again, that's not because they're not doing a great job. It's because we have to do more work and have more feedback loops at the 1.5 AU mark to understand the physics of how these structures propagate and evolve, through space.
Yeah.
Follow-up on this, very short.
Sure. Right.
And that is, have you ever had stereo flyby with the same questions? You have multiple perspectives, right?
Well, really, it's stereo A at the moment. Yeah, we've used stereo A for sure. In terms of that's one of the solar orbiters, solar probe, and stereo A have all been great assets when we're able to. But believe it or not, the lineup is there's still things that make it really tricky if you don't have a white light imager. So what I'm hearing you say is that we probably need a white light imager at Mars. That's what I heard.
I cannot do that.
Somebody should. Go ahead,
Great
Vlad.
talk, Shannon.
Yeah.
So, so the first I want to comment and then a question. So, I think that because photochemical escape, is very, very important even in early times, from early Mars, and might be was even a dominant rather than simple ion escape.
Yeah.
So might be that represents a kind of a confusing case for the Earth because, the photochemical escape, because of the escape velocity from Mars is matching the photochemical escape, right? So that's why maybe we need to be a little bit cautious about directly applying the Martian escape to the early Earth escape.
Yeah.
But my question is about, those great observations that you have shown about SCPs on Mars, and the question is about atmospheric chemistry. Have you measured like NOx's and nitrous oxide?
No, but we should, because there's an enormous community, whom I believe you're familiar with, that believe when we start to think about true habitability and thinking about life, there are a lot of good reasons to think about that being one of the precursors. When people talk about what's the spark, some people mean it figuratively and others can mean it literally. And in this particular event, some of those really high energy SCPs that come ripping in, I think it's really worth having more studies, more lab studies, and more dedicated instrumentation to look at that, because no, we have not, but that's not because we don't see the NOx. We're just not able to detect the NOx where you would need to because of where our periapsis is. And so during a deep dive campaign, that just, there are reasons that ingress and egress, basically inbound and outbound, it's hard to, with the in situ, with our NGIMS instrument, it was a little tricky to resolve some of that, but it's an incredibly important species and family for us to be looking much harder at. I highly recommend, if you're not aware, the RFI everyone's here hopefully is aware that on May 7th at midnight Eastern time, an RFI for instrumentation and basically like ideas at the moon and Mars will be due. That would be a really great slide to point out that when we think about what are game changers in moving the needle forward significantly, that's one of them.
Absolutely. Thank you.
Yeah.